Hello, in this video we're going to talk about bomb calorimetry. And so bomb calorimetry is just calorimetry with a constant volume. So many of the ideas from the calorimetry video previously still apply, but now we're in a situation where the volume is held constant. This is called a bomb calorimeter because if you have a reaction that creates a lot of gas and you're running it in a constant volume, you're really going to increase the pressure during your reaction, and hopefully it doesn't go off like a bomb. And so usually when you do this kind of work, you're igniting something. So in our little picture over here, the sample sits in here, and then you light it on fire inside an interior steel container that contains the reaction. And then now, just outside of that steel container is a bunch of water that's going to absorb the heat released by the reaction. And you measure the water with the thermometer right here. And you stir it to keep it well mixed. And so in the process of your reaction, your water will heat up, and the amount that the water heats up tells you about how much energy was released by the reaction. So the assumption here is that this is an isolated system where all the heat from your reaction goes right into the calorimeter. And you could rewrite this as Q calorimeter equals negative Q reaction. And then Q of the calorimeter is equal to its heat capacity and then delta T. And so this is technically a constant volume heat capacity because you're doing this reaction at constant volume, not constant pressure. And this is usually determined with a reference sample. To figure out what this heat capacity is, you burn something with a known energy change and see how much that heats up your calorimeter. And because the equipment here is beefier and bulkier, the calorimeter itself, the cup, as we talked about before, is an integral part of this, and you can't readily ignore it. So instead of being able to ignore the cup and just look at the temperature rise of the water, you need to now look at the calorimeter as a whole unit and determine the heat capacity for it. And then when you do this process, your delta V is 0, so therefore work is 0. And since you're not doing any work, the heat this time equals the internal energy change of the sample. So you can think of this as the total amount of energy changed in a reaction. So ultimately, when you're doing these kind of problems, you can just take the calorimeter to be the opposite of the reaction, use the given value for CV for the calorimeter, and delta T, and figure out what the heat of reaction is. So here's an example to show that process. Here we're burning 1 gram of ethanone in a bomb calorimeter, and the constant volume heat capacity of that calorimeter is given in kilojoules per Kelvin. And the temperature of this calorimeter rises some amount. What's delta U per mole for the combustion of ethanone? And so here's the equation we're going to use. Heat released by the reaction is absorbed by the calorimeter. Well, here's the calorimeter. I put it in blue because it's absorbing the heat. And so that's 2.48 kilojoules per degree C. And now this is given as kilojoules per Kelvin, but remember, we're talking about changes in temperature. And when you talk about a change, Kelvin and Celsius are the same. Change in Kelvin, change in Celsius. So I just switch this to Celsius here, because then I don't have to worry about converting the temperatures to Kelvin. I can just use them in their Celsius form. Alright, so you do this, and you find that the heat absorbed by the calorimeter is negative 23 kilojoules, which that means the reaction emitted 23 kilojoules of heat. And sig fig-wise, your delta T only has 2 sig figs, so that means your ultimate reaction heat has 2 sig figs. Like that. So now we need the energy of reaction, and thus the delta U, per mole of ethanone. And so we got to find the moles of ethanone here. So here's the grams, divide by the molar mass, and you get this many moles of it. Now we can take the heat of reaction at constant volume and know that that's equal to delta U of the reaction, which is what we're trying to find. And then we want kilojoules per mole. And so we can take the kilojoules, divide it by the number of moles, and then get an answer in kilojoules per mole. And then since we have 2 sig figs, here's the answer with 2 sig figs, like that. So this reaction releases 9.8 times 10 to the 2 kilojoules per mole of internal energy. And that's what we wanted to know. Okay, so here I am rewriting it. And I just wanted to point out that since this is a constant volume, heat changes here do not equal enthalpy like we had before, because internal energy and enthalpy are only the same if the change in pressure and volume are zero, and well, while the change in volume is zero in the Baum calorimeter, the change in pressure is probably not going to be zero, especially if you're doing a combustion reaction which releases gas, usually. And so we're finding internal energy, not enthalpy. Now these energy values are used in lots of ways. The most common way that you see is the calorie listings on the back of foods. Calorie is the English unit for energy, and so we're using joules. 4.184 joules is a calorie with a lowercase c, and then 1,000 calories is calorie with an uppercase c. And so here we're listing uppercase C calories. And really what they do is they burn this in a Baum calorimeter and figure out what the energy change is and convert that into units of calories and then figure out how much energy is contained in that food. And the reason why this is appropriate is because when you ingest and metabolize the food, the reaction is very similar to a combustion reaction. Obviously, it's not lighting a fire in your belly, but the overall reactants and products are very similar. And so thinking about a combustion reaction and measuring the energy released by that is a good gauge of how much energy is released by the food when you eat it. Okay, then the last thing I have for this video is the equation flowchart for chapter 14. And so I first made this document when I first learned the material in order to teach it and got really confused myself as to how all these equations fit together. So ultimately, everything we've done in this chapter comes from these four equations at the top. And then we just mix and match them in so many different ways and use a bunch of concepts and ideas in order to get different things done. And that's the part that's confusing. But overall, we just start with four things. We start with this fundamental idea that internal energy change is equal to heat plus work. Those are the two ways that your system is going to exchange energy. And then we use this version of work that we're only thinking about gas expansion and contraction work. So work is equal to negative pressure times volume. So if you combine these two together, then you get this equation here. And then, well, PV equals nRT, so you can get this version here, assuming you're at a constant temperature. And then we defined at constant pressure that Q is equal to delta H, so you can get to this version of the reaction if you want. Or if your change in number of moles of gas or your change in volume of gas are zero, then this term drops out, and you're left with just delta U equals heat. This is what we said. If you're not changing volume, delta U is heat. The other thing we did is we defined this new function enthalpy, which we can write in either this form or this form down here. And then if you use this equation and combine it with the equation here, you can get that delta H is equal to heat at constant pressure, which is what we've been using all through calorimetry. Now, in both these cases, if your change in volume is zero and your change in pressure is zero, then you can say that the internal energy, the enthalpy, heat at constant volume, heat at constant pressure are all equal to each other, because if there's no change in pressure or volume, no work is done, and you're just looking at heat. Okay, so we've been through all that. And then this is the calorimetry idea. So you have heat is equal to the heat capacity change in temperature. Then you have different forms of heat capacity. You can trade this out with the mass times the specific heat. And then when you're doing calorimetry, you're thinking that your heat absorbed or released by your overall calorimeter system is zero, in that heat is just transferred from, say, your reaction to the water it's run in, or to the calorimeter or something. Right, so heat just goes from 1 to 2. And then if you're at constant volume, you're always generally using the calorimeter equals the reaction. And if you're at constant pressure, you can do that same thing. The calorimeter is equal to the reaction with a sign difference. Or you can ignore the calorimeter and say this is pretty much equal to just the heat absorbed by the solution, which is what we often tend to do, and what we did in the examples in the previous video. So then the heat at constant volume is delta U, the heat at constant pressure is delta H, And then, again, if you're not changing gas volume, that these are all equal to each other. So that's how all the equations work together. It is always better if you can get a holistic sense of how all these pieces fit together. It helps make it easier to understand. And do what you can do to try to get there. And in the meantime, that's all I have for this video. So thank you very much for listening, and I'll see you in class.